Okay. Stay up there. What are you doing? If I put a current through that loop of wire, you're going to create a magnetic field. Is everybody okay with that? Okay. So does it make sense to you that if I take a piece of, so I make my wire like this, and then I put the current in one end and out the other, which way is the magnetic field going to go inside that loop? Like kind of up or kind of down? So now, I'm not talking about force. I'm talking about magnetic field and current. So you should be using open or closed rule. Closed. You should wrap, in your mind, reach out and wrap your fingers around that wire. It's supposed to be laying flat, like in front of you. So this is supposed to be flat. So if this is flat, is the field pointing up or down? Down. So this is that loop of wire like looking from the end. Do you get it? Like looking from down here. So you can see the ends of the wire right there. And then the current is going out here and into there. So the current's going in here and out there. So the current's going like this, then it goes around the back, then it comes back this way. Is that making reasonable sense to everyone? Okay, it's kind of a weird drawing, but yeah. Now, show me. Oh, I should have put that slightly differently. Okay, well, in this position, the magnetic field going through this, does it make sense to you that the magnetic field caused by that wire is going like this? Right? Like it's like here, and then on the back over there, it comes like this. Right? And then here, it's like that. So it's like everything going through the middle.
Is it because when you grab it, your fingers are...
Yeah, exactly. Okay. Now, so just to make sure everybody understands that part of it. Now, if I take this thing that I've concocted, oh, come on, this is gonna be nasty. Oh well. Let's see, how does I do this? Yeah, okay. So if I take this, let's see if I can group this. Yeah. Put this over here. And then I will redraw the magnetic field lines like this. And then I take this. If I take this thing and I go like that, tilt it. Current's still going in that way, right? Everything's just like normal, but now it's parallel to the field lines. Pretend or draw your attention to this position right there on the top, where the current is in the wire going away from you. And I want you to tell me, how does the field affect that wire at that point? So remember, now I'm asking you, how does the field push the wire? How does the field push the wire at those 2 points? How about this? We'll say A, B, C, or D, none. Oh, good. So is it pushing towards A, towards B, towards D? None, not pushing at all.
Especially the field or the...
Yeah, what is the field doing to that loop of wire? Is it pushing it towards A, pushing it towards B, towards C, or is it actually not pushing it at all? You know, about 5 more seconds. And we're done. Okay, so tie for B and 5, or B and none at all. All right. So, please, everyone, take your right hand and point your fingers in the line of the magnetic field. See the green lines? That's the magnetic field. Put your fingers in line with the magnetic field. So boom, your hand should be up like this. Whether it's like this, we don't know. It should be up like this. Straight up. Do you understand why that is true? Is everyone okay with that? It's not like this. It's like this. This is when I asked you, what does the magnetic field look like around the wire? Now I'm asking you, which way does the field push the wire? Boom, you gotta do this. Okay, so now, up here, where is the current? Towards you or away from you? Away from you. And thus, we have a force in that direction, towards C. Okay? Now, same. A, B, C, or D. Please tell me, which way does it get on the bottom? A, B, C, or D? Which way does it get pushed on the bottom? A, B, C, or D? Can you answer?
I've just done it twice too.
Hang on, let me reset it just to be clear. Yeah, okay, it should be going. Can you vote or no?
So it's the first on Sunday.
Okay, let me do this. There, how's that? There you go. Now it's working. So A, B, C, or D? And here we go. And most people said A, and those people are correct. Because my fingers are still pointing up, but now on the bottom, it should be pointing towards you. So this, do you see that if you push something like this, what's going to happen to that object? Yeah, if you walk up to Richard and then push this shoulder, pull that one, he's going to rotate around this point. That's why this is about torque. And the equation for torque is NAIB sine theta. This NAIB doesn't change. That's based on the number of loops. How many loops? One. Right? There's one loop. They give you the radius. Well, actually, we can go back here and take a look. The radius is 4 times 10 to the minus 2 meters or 4 centimeters. So you can use that to find the area. And the B is 2.2 Tesla. Now, here's the fun part. What is theta? Okay, and so as Ben said, the angle here, and everybody's going to wonder, why are they laughing? The angle here is theta, in this case, is 90. And he figured that out using logic by saying, here is the torque, right? That's the torque caused by this magnetic field. And that is maximum because the force and the radius are at 90 degrees. So if this is the position of maximum and this is the max value, if theta was 0 or 180, then this would all be 0. But it's obvious that these two are going to be max. So then, therefore, in this case, theta must be 90. So how do we kind of wrap our heads around this? It goes like this. When you have a surface, or when you have a loop, or a square, rectangle, whatever, you don't describe it or its behavior by the plane of the loop. You describe it by the perpendicular of the loop. So if I point my pen like that, that means that this is like that. If I point my pen down, that means like this is pointing down, right? You use a vector to describe the behavior of the surface of an object. That vector is always perpendicular to the surface. And that's why theta is 90. Okay, so for example, your desk, we would say this describes the orientation of your desk. So if the magnetic field in this room is pointing from floor to ceiling, then that means theta for the surface of your desk is 0. And if we looked at it here, we can see that also like this. If I do this, do you see that that theta is 0? Okay, that theta is 0.
Is it the same force that way?
Because if I take this loop, the theta is not the plane of the loop. It's not the loop in the field. It's the perpendicular to the loop and the field. I mean, you can always think about this is about torque, and torque is like that. Torque is going to be perpendicular to the radius. So the theta is always going to be the angle between this and the magnetic field. If you want to think about it that way, it's another way to think about it. But honestly, the best way to think about it is just to realize that when in physics, when we're talking about a loop or an area, and we want to describe the behavior of that area, we don't use the area. We don't use it as the descriptor. We use the vector that's perpendicular to it. I don't want to explain the whole why of that because it has to do with cross products and junk like that, so don't worry about that. But now, what that means here, show me with your, what is the effect of the magnetic field on the loop when the loop is perpendicular to the field? The answer is 0. There is no effect. Part B, what is the effect of the field on the loop if the loop is parallel to the field? This is like part A. This is like part B. That's parallel to the loop. That's the field is, here the field is perpendicular to the loop. There the field is parallel to the loop. So for part B, it's just NIAB because theta is 90 degrees, sine is max. And so for C, remember, we're talking about, when we talk about theta, we're saying that theta is the angle between the field lines and the perpendicular. So if I take this and I rotate it to 15 degrees, do you see this is the perpendicular like that? So what is the angle here? If I tilt it, if this is 15 degrees right there, what's that angle right there? Yeah, it's 75 degrees, right? 90 minus 15. So we use 90 minus 15. Actually, you could also use 105. Do you see that? Right here. That's 105. So you could use 75 or 105, plug it in, and you'll get your answers. So your two answers are 5.5 times 10 to the minus 3 or 5.3 times 10 to the minus 3.